Good afternoon, everybody. Thank you for joining us for today's webinar. Before we start, I would like to give other participants a few minutes to join. So I think we will start in about 3 to 4 minutes. Good afternoon, everybody. Thank you for joining us for today's webinar. It is the fourth webinar in our webinar series on World Space Week, which has a theme of celebrating women in space. As in the previous webinars, we are running a competition where a winner can get a SANSA goodie bag. And in each webinar has a question. And today's question is, what is the process through which the magnetic field in space plasmas reconfigure to release energy? The question again is, what is the process through which the magnetic field in space plasmas reconfigure to release energy? You can email today's answer as well as the answers to the other questions related to the other seminars or webinars to spacesci-info@sansa.org.za. The information is also given in the chat box. So today's webinar is on all things data, data stewardship, interpretation, and dissemination for science advancement. We have 3 speakers on our panel today, and the first speaker is Ms. Kate Niemantinga, who is a data acquisition practitioner at the Space Science Directorate of SANSA, where she is responsible for the data produced by the South African Remote Sensing Instrument Network. She has a bachelor's degree in computer science and has 2 decades experience as a senior SQL developer and data analyst. Kate, welcome, and we look forward to your presentation.
Thank you, Dr. Zama-Katamzi Josef, for the introduction. Just going to share my screen.
So while Kate is doing that, maybe I can just say if people have questions, can they please post them on the chat box, and at the end of all the presentations, then we will ask the panelists to address those. Thank you.
Zama, can I ask that if you can see my screen?
Yes, yes, we can see your screen.
Thank you. So yes, good afternoon. My name is Kate Niemantinga. I'm the data acquisition practitioner within the engineering and data acquisition business unit at SANSA Space Science Hermanus campus. SANSA Hermanus was up until about 10 years ago known as the Hermanus Magnetic Observatory, which was founded in 1940. We have geomagnetic data sets from that period onward, which makes it one of the longest standing magnetic observatories in the world. We actually have data from the Cape of Good Hope from the 1840s. The magnetic observatory was moved to Hermanus in the 1940s with the electrification of the train lines. As you might know, Hermanus has a train station, but it has no train lines, and therefore it has a magnetically clean environment. The underlying, excuse me, the underlying geology of the area also consists exclusively of Table Mountain sandstone, which has negligibly small magnetic gradients. So this enables us to host various instruments here on our Hermanus campus. We have around 14 instruments here, whereas our entire geomagnetic range of instruments is about 90 instruments. And they are different types. So we have geomagnetic, ionospheric, and magnetospheric instruments. These instruments are placed around Southern Africa, as well as the high latitude observatories on the islands Marion and Gough, as well as at Antarctica. These instruments are used in a variety of applications. Our data sets are also used in fundamental research or blue skies research, and a variety of industries make use of our data, such as mining, the defense force, maritime sector, underwater exploration, the space industry, both private and commercial aviation, and predicting environmental hazards. Currently, SANSA remains the only facility in Africa that calibrates magnetic sensors for dynamic platforms, such as unmanned aerial vehicles and satellites. The facility also develops biannual geomagnetic field maps that contribute towards navigation and positioning applications within Africa. With the onset of the 4th Industrial Revolution, space data is becoming more and more important in understanding how a magnetic field is affected by the sun and how it affects our satellites, GPS, and other relevant technologies. So the data that we have collected is provisioned on a data portal or platform called Sandims, which stands for the South African National Geophysical Data Instrumentation Management System. It's quite a mouthful. But for far too long, the data collected by the SANSA Hermanus facility had been fragmented and very difficult for international researchers to find. So it basically works on the same principle as an e-commerce shopping site. One can browse for the data that you want. You can see relevant metadata attached to that data sets, and then put it in your shopping trolley and check it out. Data is free to use for pure academic research. One just needs a user login and password. We also have about a dozen instruments in Antarctica. The EDA business unit is responsible for sending 2 engineers to Antarctica every year for 14 months. And that means they overwinter there. We also send 1 engineer to Marion Island. These engineers are responsible for ensuring the instruments are operational and collecting good data throughout the year. As any good data practitioner will tell you, bad data is worse than no data. Our flagship instrument at Antarctica is the SuperDARN radar, which our next speaker, Dr. Judy Stephenson, will be talking about. So here are some lights from way down under. The SAA Gullis 2 is owned and operated by the Department of Environmental Affairs, takes a team down to Antarctica fully loaded with supplies for the year. The base is called the SANEA 4 base. So it's the 4th South African base built down there, but it's the first base that was actually built on above ground and on stilts. So the previous bases were all built on the Informal ice shelf and were subjected to basically gradual snow buildup and eventually would be crushed by the weight of that ice. This base has been built on stilts so that the snow can blow away from underneath, thereby prolonging the life of the base. And this design was revolutionary at the time. In our next slide here, we have the islanders busily shoveling snow into the smelter for their drinking water. This smelter is affectionately known as the Smelly, and all waste products, food, sewage, and other waste needs to be sent back to South Africa. As the old saying goes, gather all the memories, but leave nothing but footprints. A tradition in Antarctica is to have a snow bath on your birthday. Here we see the SANEA 57 team member Stefanus Kuman having his. And many thanks to Stefanus for sharing some of the photos you are seeing here today. The aurora is the name given to the light emitted when the upper atmosphere is hit by energetic charged particles, principally electrons from the solar wind which travels along the Earth's magnetic field lines. Truly a beautiful picture and one that one can be very privileged to view in Antarctica. So my path in getting to the place where I am now is I studied a bachelor degree in computer science through UNISA. I worked while I studied and have done many Microsoft certifications. More recently, I'm doing AWS certification, ISO 9000 certification. I'm also personally studying Aldama DMBOK, which is the principles of good data management. Data stewardship is a hot topic or potato, depending on which circles you run in, but there are lots of factors to consider. So the open access data movement being one of them, POPI Act, and then actually taking care to ensure good quality data meets the end user. At SANSA Manus, because we have so many different types of data, there are various issues around provisioning the data in the format the end user can use and decipher, collecting, maintaining relevant metadata, and then the need to be able to understand and use some of the software that is needed to manipulate the data sets into readable formats. Metadata standards are also becoming more relevant. There are many, many different metadata standards. So it's complicated, but it's very interesting work. I'm also part of the SCADM group, which is the Data Management Working Group associated with the Scientific Community of Antarctic Research, or SCAR. I've taken part in the SCAR conference in Kuala Lumpur. I've been a delegate at Kyoto University in collaboration with DAGSM in Japan. I'm on various networks such as Intermagnet, Open Repositories, CoData, Data Alexa, Research Data Alliances, and others. It is very important to keep current. SANSA also forms part of other international networks such like Intermagnet, Demogrape, VLF Network, the SuperDARN Network, Ryometer Network, DIDBase, Willen, World Data Systems, and Gloria. Oops. Since the advent of the space age in 1957, South Africa has established a reputation for accuracy and reliability in the international space community. We also have a long-standing history of supplying high-quality geomagnetic data to the international scientific community. Today, SANSA is using the benefits of space science and technology to help grow and develop the African region as we move into the fourth industrial revolution. I thank you for your time.
Thank you, Kate, for that lovely presentation. Our next speaker on the panel is Dr. Judy Stephenson, who is a member of the SANEA HF radar experiment team, which is the South African part of the international group HF radar network known as SuperDARN. Her job entails research with the SANEA HF radar and other SuperDARN radar data and supervising postgraduate students. SuperDARN is an instrument that provides a window into space, and as such, her field of specialization is the magnetosphere and its interaction with the solar wind and neutral atmosphere. In addition, she manages the data from the SANEA HF radar and is responsible for the installation and maintenance of the radar software, which runs on Linux servers. Dr. Stevenson, thank you for giving this presentation, and we're looking forward to hearing what you have to say.
Thanks, Dr. Katamzi Joseph, for that nice introduction. And yes, I'll be talking about tracking space weather with SuperDARN. As you heard already, SuperDARN is a flagship experiment of SANSA. And if you've probably never, it's a flagship experiment and it's an international experiment. It involves 11 countries and we are part of it, so proudly South African. And probably you've never seen space weather because you have to go to polar regions to see it regularly, although it has been seen in South Africa. So here's a picture of space weather. Beautiful auroral lights, and it's taken at the South African Antarctic base called SANEA. And you can see in this picture, these lights have a structure, and this is showing you the Earth's magnetic field. The Earth's magnetic field is produced by molten iron currents below our feet, and this is almost the only time that this is visible to us. So what's cool about science, we get to understand things that normally you don't see. So as I say, mainly it occurs in the polar regions. So this is an image taken from a satellite from space. Here's the Antarctic. And this aurora normally occurs, or always occurs, in a ring. Now this ring is because of the actual morphology or structure of the Earth's magnetic field. The aurora in the south is called aurora australis, and the aurora in the north is aurora borealis. So I'll be answering these questions. What is space weather? Why do we study it? What is SuperDARN? And give you just 2 examples of how we track weather with SuperDARN. So as you know, the sun is a nuclear fusion reactor, and so it is a very hot place. And around the sun is a halo of very hot gas, up to 1 million Kelvin, produced by magnetic processes. This gives the particles, or plasma, which is charged particles, a gas of charged particles, it gives it enough energy to escape the gravity of the sun. And it blows out constantly in what we call the solar wind. So here we have the solar wind, it encounters the Earth. This is the Earth's magnetic field. And usually we're mainly protected from all the radiation from the sun due to the Earth's magnetic field. But this field is actually quite leaky. So we do get some through, and in particular, certain space weather events called a geomagnetic storm can actually puncture a hole in the magnetosphere. So these are the types. So when you look at the sun normally from day to day, it looks pretty constant, but actually there are these areas of activity called sunspots. And these can produce flares. Here is a flare in the, let me just put on my pointer here. in the X-ray spectrum. And these flares can produce doses of X-ray radiation and extreme ultraviolet. They also produce energetic particles. But a more interesting event and the kind of hurricane of space weather are what happens when that corona, which is the name for the halo around the sun that's super hot, when that becomes unstable, it belches out like a gas of very, very hot particles, charged particles. And this is called a coronal mass ejection. And it leads to a geomagnetic storm. And the reason that that happens is I'll explain later in the talk. But I'd like to show you a little video here of this process of the geomagnetic storm and how it leads to an aurora. So here we have the active sunspots, and somehow the flares cause this corona to become unstable. It kind of ejects this big cloud of hot plasma, which can encounter the Earth. And as it does, it has a special way, this type of storm, of opening this field line of the Earth and actually entering. And as it enters and sweeps back, as you will see, it opens those field lines and it pulls them back into a long tail, a bit like a windsock. And then at some point, again, you see a special process here, a magnetic field process, which actually releases energy onto the particles that are associated with this field line. And these particles flow down to the Earth. And you can see here, they actually hit at high latitudes and form the aurora. So they'll hit the atmosphere and cause the neutral molecules of the atmosphere to become excited, and they emit beautiful light. So why do we study space weather? Well, of course, it affects our satellites and all our space-based technologies. It also affects the aviation industry, and it affects all our communications, in particular GPS. But the most important effect of space weather is that in these regions where a lot of radiation comes in, it causes a lot of changing currents in this charged layer above the neutral atmosphere called the ionosphere. And these changing currents cause the Earth's magnetic field to change rapidly. And we know from first year Faraday's law, a rapidly changing magnetic field will induce a current into any conductor. And what long conductors do we have but power lines? So this causes power surges, which blow transformers. And it has been on several occasions, quite widespread blackouts in Canada, Russia, Scandinavia. And we have had transformers blow in South Africa. But also what interests me is recently someone brought up the fact that our internet is very vulnerable to space weather because our internet is all connected simultaneously, almost by fiber optic cables. And these actually need repeater stations, which needs power, and electronics, smart electronics. And so these are vulnerable to solar storms too. So it's not impossible that we could have an internet apocalypse. So what is SuperDARN? This is the third question. So put quite simply, it is a network of high frequency radars. So here's the network in the Northern Hemisphere, here in the Southern Hemisphere. And of course, they're mainly in polar regions because, as I explained, that's where space weather mainly happens. But now we are starting to see a lot more radars being placed at mid-latitudes here in Australia and Japan and in the United States in order to catch it when the auroral oval spreads more to the equator during active periods. So here's the SANEA radar sitting here, and the fields of view of these radars are like a slice of cake, and they're very big, and I'll explain why. So what does one look like? Well, our radar looks like this. It's a twin terminated folded dipole. So this is the actual antenna, these black lines. And the white lines are actually stay ropes that are keeping up the masts. So as you've heard, every year we have to take down an engineer by ship to look after our radar. So how do they work? Well, they transmit high frequency radiation, which means in the megahertz range. And we do that because that radiation is bent in our ionosphere. So it can be bent by the density of the charged particles, okay? So it can be bent so much sometimes that it will be bent down to the ground, even come up again to the ionosphere and return to the radar. That's why these radars can see so far and have such big fields of view. But let's just concentrate on, say it bent just in the right amount to become 90 degrees to what we call these irregularities. So the ionosphere is full of like waves, like instabilities, because it's constantly disturbed. It's a bit like throwing a pebble on a pond. You always see ripples coming out. And so these irregularities can act as targets to be reflected. And one of the main things we want to know in space weather is how all the charged particles, the electrons, are moving around up there, because how they move around tells us what's happening deep into space, because they are connected by the Earth's magnetic field to processes deep into space. So we would be interested in the velocity of these charged particles. So we know also from first year physics, you might recall the Doppler effect, where if sound is reflected or emitted, or any radiation is reflected or emitted from a moving object, it changes its frequency. So if we emit a known frequency and we get a slightly lower frequency back, we know the object is moving away. And if it's slightly more, we know it's moving towards us. So if we have all these velocity measurements, we can put them on a map like this. So these are velocity measurements from all the radars, all the different radars. And this is a map for the Southern Hemisphere. There's an equal map for the Northern Hemisphere, which I'm not showing here. But this map is during a very active period where space weather is enhanced, and here is a quiet time for space weather. So let's just focus on the map on the left here for the time being. And you'll see it's taken every 2 minutes. It's given every 2 minutes and published. It's the only ground-based space weather map in the world. And this is at 12 UT, but of course the local times are all plotted around the circumference here. Here is midnight, here is midday, so the sun is at the top, and the solar wind is blowing more or less this way. Okay, so these Doppler velocity measurements are analogous to if you see a meteorological weather map on TV, that would be analogous to wind speed. Okay, so this is now the speed of the charged particles. And here's their color bar here. So the red is the highest, so the red will have the longest tails here. And then these all these measurements are fitted to a known model. And the model is written in these solid lines here. So the model constrains to fit the data. And these solid lines are lines of equal electrostatic potential. So of course, the high flows are going to go along an equal potential. So here we have the lowest potential, here we have the highest. And the difference between these two regions is written here, 72 kilovolts. So that is a measure of how much energy is being input from the sun into the polar ionosphere. So you can see here that this blue cell is actually rotating clockwise, if you look at all the vectors, whereas the red cell here is rotating anti-clockwise. So how do we interpret that? So in order to interpret that, we need to have a look at this sketch here. Here's the Earth. Drawn here are the auroral ovals, ovals of light, and this is the Earth's magnetic field. On the left here would be the sun, and the solar wind is coming along. Let's say in this instance, it's a coronal mass ejection. So we have a geomagnetic storm. In that instance, the solar wind's magnetic field is in an unusual orientation. It's orientated down. Normally, it is orientated upwards, northwards, you would say. So when it encounters the Earth's magnetic field, the Earth's magnetic field here is coming out of the south, coming up here. So they are orientated in an opposite directions, those two magnetic fields. This allows a process, what is called magnetic reconnection. When two magnetic fields meet who are exactly opposite direction, they can reconfigure like this and release a lot of magnetic energy. And where does that magnetic energy go? It mainly goes to the particles associated with the field line. So they get like a rev of energy. So if we had to trace this field line from one, suddenly this closed field line here becomes open. And now the solar wind, all those particles on that field line can actually gain access to the polar regions. So as the solar wind blows from left to right, these field lines move 2, 3, 4, 5, 6. The same is happening in the south. Again, we have a special point here, whereby again, the two fields are in opposite direction. The field in the north is going towards the Earth. The field in the south is going away. Again, this process of magnetic reconnection happens. Another big dose of energy gets given to the particles for the second time, and they can flow down the field lines here to the auroral oval and give us a display. Of course, these field lines also have to move to the front. So they have to go 8 to 9, because if that wasn't the case, when the coronal mass ejection comes, it could totally strip away the magnetosphere, which does not happen. So if we look down from the poles, you can see these events from 1, 2, 3. So you can see the velocity going across the pole and comes round in a cell back again, back to 9. So here's one cell that is clockwise. On the other side will be a cell that is anti-clockwise. So that is what we are seeing here. At the top here is a key of the solar wind magnetic field. And it is showing you with this arrow pointed down that its orientation is different to the Earth's magnetic field. On the other hand, on the map on your right, during quiet time, you see a much smaller auroral oval. You see the cells are breaking up, not obviously two. And now you're seeing that the Z component of the solar wind is actually pointing upwards, which means it's more or less the same. So finally, I thought I would show you an instance of space weather from one radar. So of course I picked the SANSA radar. And this is a phenomenon of space weather called a traveling ionospheric disturbance. So these are quite large waves within the ionosphere of electron concentrations. So if we were to look at the radar's data at any one time, this is at 8 o'clock UT, you would see here a lot of backscatter. Okay, this is backscatter power. So here we get the maximum backscatter, here the minimum in blue, And here, no backscatter at all because there were no irregularities. So here I've plotted just one beam. So you can see this is a very blocky here, which means the radar's data is actually in beams. So it looks at one beam at a time. And then after 2 minutes, it goes back and looks at the first beam again. So if I take one beam here and plot it for a whole day, 24 hours, versus range, so that's this distance from like that. So this would be 3,500, which corresponds to the top here. Then you would see that there are these striations or enhancements of power periodically like this. And this is a traveling ionospheric disturbance. So this is caused by a number of things, but mainly heating in the polar ionosphere. And this interferes with our communication with satellites, and of course causes error with our GPS and GNSS. And it is also important in climate because it's vital in vertical transport and equatorward energy and momentum transport. So that's just two ways that SuperDARN actually monitors space weather, and I hope you got something from the talk and enjoyed it. Thank you.
Thank you very much, Dr. Stevenson, about that overview about SANEA, as well as the science that one can do with that instrument. Again, I'd like to remind everybody, if they have questions, please put them on the chat box so that our panelists can address them later. So our final speaker for today is Ms. Naledzani Mudau, who is a remote sensing scientist at SANSA, where she leads research on the development of human settlement products and services from satellite imagery. She uses her 15 years experience in the remote sensing and GIS fields in her research, as well as in actively working with government departments and other end users, including local municipalities, to demonstrate the use of Earth observation data in decision-making and reporting. She is a co-chair of several working groups in Earth observations, and these groups promote the use of Earth observation and geospatial technologies in government and to support the attainment of sustainable development goals, in particular relating to urban development. She also participates in EO for SGD and Human Planets Geo initiatives, the latter aiming to support novel evidence-based assessment of the human presence on the planet Earth. So without further ado, please, Ms. Mudau, you can start your presentation.
Good afternoon, everyone. I'll just switch on my video, just so you see where I am, and I'm going to switch it off to make sure that any bandwidth. So I'll be talking on how data can be used to support development of sustainable cities. My presentation will focus more on Earth observation data. Okay. Urbanization is usually linked with the development or improvement in human capital and also economic development in countries. And unfortunately, in Africa and many developing countries, urbanization is linked with or results in informal settlement development, overloaded infrastructure and services, increased inequalities and poverty. There are a number of initiatives in countries and globally that are aimed at improving the lives of people in the cities and also in general. So those are looking at, for example, in South Africa, transformation of human settlements into sustainable cities, and also providing basic services that are required. If we look at the SDGs, for example, number 11 is looking at building sustainable cities and human settlements. All these development agendas can only be successful if we have relevant current and historical data and information to support planning. So if we look at the traditional sources of data, they usually involve people going on the ground, for example, in ground surveys, where people go on the ground and acquire information on demographics and also on the living conditions of people. So most of the time, the data that is used for planning and monitoring, if we're looking at urban planning or spatial planning, it's usually acquired through censuses or ground surveys. So that information is crucial because it gives us an understanding in terms of how many people live in particular spaces and how they live. Unfortunately, this exercise of ground survey requires a lot of resources, which then results in, then we need to look at other data sources. Technologies and advancement in technologies, there are now many data sources sources of data and information that we can use to plan our cities so that they become sustainable without compromising the natural environment. So such sources include social media, smart sensors. In some cases, of course, we still need to send people on the ground to collect information. And most importantly, or one of the most data sources or most important data sources is the one that we acquire using remote sensing, which could be using platforms such as drones, aircraft, and also satellites. So the presentation will be showing more or illustrating how we can use Earth observation data to gather information that can support sustainable development of our cities and human settlements. Thanks to the advancement in Earth observation technology, we are now able to acquire data at very high spatial resolution, which allows us to see a lot of detail in terms of what is happening on the ground. So the picture that we're seeing is an image taken by a drone over some area in Pretoria. So you can see, so this is an informal settlement, and you can see the spatial distribution of the dwellings, and we can also see location of trees and paths, cars. So we can now get data which is up to like few centimeters, which was not possible in the past few decades. This allows then urban planners, authorities to have access to information that they can use to support planning and decision making. So traditionally, if they were to send people on the ground, it would take a lot of time, but also due to accessibility of some of the areas like informal settlements, most of the surveys don't even, or people who are doing surveys don't even enter such settlements because of safety. So now the authorities will have access or have access to imagery or data sources that they can use to independently even verify some of the projects and some of the information that they might be getting through report. So in addition to medium to high spatial resolution data that is available, there's also this kind of imagery that can support planning, and also evidence-based decision making, which is important and crucial to for us to achieve the sustainable development goals. So if we look at how the data from Earth observation technology can assist us, we can measure urbanization in terms of the expansion, densification, amongst others. We can map and the location of informal settlements and derive or develop necessary policies to manage them. Earth observation data products can also be used to support spatial planning. This is where we're looking at which areas require what kind of services, which is if the authorities are only dependent on the census data or survey data, they might not have a good understanding of what is happening on the ground. So integrating the information collected through census and ground surveys together with Earth observation data, then authorities and decision makers will have detailed information or enough information that they require to make spatial evidence-based decision. So that will ensure that the planning, also looks at what is possible to, what is likely to happen in terms of the usage, the demand, amongst others. In addition to spatial planning, we can also use the data to monitor the development projects, which is also very important because most of the time the projects are developed in silos, where then a provision of services it's an afterthought. So once the relevant authorities have access to the data that we derive from satellites or Earth observation technology, they can then make informed decisions in terms of where they need to establish or provide services. In addition to spatial planning, we can also use Earth observation data for disaster management, including health disasters like the pandemic that we're dealing with. Earth observation data provides information on the location of where people are, and we could also then assess the density. As we all know, social distancing, for example, is still the main measure or one of the measures to manage COVID-19. So with the imagery, we are also able to identify the settlements where social distancing will be a challenge, which are mostly informal settlements. So, and also we can use the imagery to also assess the impact of the developments. There are many areas where development is taking place in agricultural prime land and environmental sensitive areas. So that information or that analysis can only be done when we have access to Earth observation data, because it allows us to see the land use in the different areas, and we could also go check historically. So which helps because many departments that are mandated to do such analysis, they cannot have enough resources to go check each and every area that is being developed to see if it's not compromising the natural environment. So we are also using the data, Earth observation data, to support reporting of this development agenda. So because with Earth observation, we are able to see what is on the ground. So it means that the information that we are able to derive, it can be used to provide evidence in terms of how people are doing or cities are doing in terms of building sustainable cities, and also providing the necessary services that they need to provide to communities. So data helps us understand the status quo in terms of where the settlements are, the different types of settlements. For example, the picture shows the different human settlement types around Johannesburg City region. from your formal residential areas to your townships and informal settlements. So understanding the spatial distribution of settlements and where people are can then help in terms of planning of the services that people require. For example, if we're looking at transportation, we can identify where people are and potential routes that will ensure that people don't travel long distances trying to find transport. And also if there are developments planned, for example, for economic development, amongst others, then the decision makers can see where those needs are in terms of making sure that they reach the target people. So with the imagery, because we have access to historical data, we can then go back to 1996, for example, and see the extent of our cities or settlements, and then assess the growth from then until, for example, 2014, where we'll be able to see how the cities are growing and assess if there is any particular trend that we are seeing on the ground, which can then inform the future planning or the planning of future services and also approval of land use activities. So this is just to zoom in, illustrating the very same concept of understanding urban growth using Earth observation data. So here we assess 2006 to 2014 using spot imagery, and we can see the developments in red. So this rapid development, if it's not taken into consideration or it's not noticed and quantified, it can result in a lot of disturbances on the services. For example, if we're looking at electricity, water, if these areas are not seen in advance and planned and services planned for accordingly, it can result in a lot of issues around there, including load shedding, for example. So we can use data to assess how our cities are growing, expanding, densifying in the country. So as we may be aware, a lot of development or a lot of urbanization will be taking place in the cities and small towns, especially in the developing countries. So it is important that we continue to monitor our cities. But what is also interesting is that since the big cities have been there around, and the land use for development is also limited. So we can see that a lot of our small cities like Polokwane and Rustenburg are the ones that are experiencing a lot of expansion or high expansion rates compared to the metropolitan cities, because they still have space. But what is important is that the authorities, they look at the expansion and manage it, because if it's small cities, there might not be a lot of focus in terms of assessing the impact of development on the environment. But once we present the changes on an image like this, then we are able to advise, and also the authorities will be able to see the areas that they need to focus on. As you may be aware, South Africa is dealing with or has a challenge of informal settlement development, where a lot of people, especially around the cities, are struggling getting affordable rental houses. So they end up settling for informal settlements. These areas or settlements are located at high risk, environmental high risk areas where they are affected by floods and other natural disasters. So it is important that the authorities like the National Department of Human Settlement is aware of the spatial distribution where these settlements are located so that they can make necessary plans in terms of upgrading them. So one of the challenges that the authorities are faced with is just to understand where they are in terms of having a national database of informal settlements. So with the Earth observation data, we are assisting them to derive such a database based on high resolution imagery. So the map shows the spatial distribution of human settlements and also informal.
Nale, it seems we've lost you. I think we've lost our panelist, Ms. Nale Mudau. If maybe we can give her like a minute or so to come back on again and see if she can continue the presentation. Nale, can you hear us?
I can hear you now, but I don't know when you lost me.
You were in your last slide, I think you were talking about informal settlements being located in unsafe places. Yeah.
Was it on this slide?
I think the previous slide, let's see. No, it wasn't on the slide, it was maybe the previous one.
Okay. Maybe, okay.
Yeah,
I can just continue from here.
Okay.
Okay. So this map shows the spatial distribution of informal settlements in the country. One of the challenges in terms of access to data is location of informal settlements, which then makes it hard for the department to plan and reach out to all who require assistance in terms of adequate housing and access to services. So this graph shows the spatial distribution of or the proportion of informal settlements in the country per province. We can see that Gauteng has the highest number in terms of informal settlements and also in terms of the area that is covered by informal settlements. And then this graph on top then shows then the increase or the change in terms of informal settlements development in the country from 2006 and until 2020. So we can see that the development of informal settlements is in the rise. So this information, together with other information from surveys such as census and ground surveys, can then assist in terms of decision making on how we want our cities to look like in the future. In addition to supporting planning, the data, Earth observation data can also be used to monitor the development projects like informal settlement development project, informal settlement upgrade project. I think that's the program, that's the name of the program that the National Department of Human Settlement has to upgrade informal settlements. So we can monitor the informal settlements that have been upgraded or progress made in terms of upgrading the informal settlements using data. So this information can also be used then to look at whether the upgraded settlements have access to the services that they require, like education, health facilities, economic opportunities, amongst others. We can also use the data then to support forecasting efforts and also reporting, as indicated in the previous slide. So we can integrate the data that we get from Earth observation technology with demographic data to understand, for example, energy consumption in particular cities. So this information can help the future demand of services. So if taken into consideration together with other relevant information, then the authorities will be able to make necessary informed decision in terms of planning of the services that is required to ensure that the cities and human settlements are sustainable in terms of access to services, and also making sure that the environment is conserved and the development does not compromise the natural environment. So the use of data in shaping our cities or its contribution to building sustainable cities has been recognized by international bodies like Group on Earth Observations, CEOs, as crucial in terms of decision making. So this picture just highlights some of the global human settlements data sets that are recognized as or that are available to support planning and monitoring of development agendas, especially when we're looking at the SDG 11, which is looking at building. I hope I managed to share with you or to show you the value of Earth observation data in building or shaping the future of our cities or our future cities. Thank you for your attention.
Thank you very much, Nale, for that interesting presentation, especially just the education of how Earth observations data can be useful for planning and improvement of our development of our nation in terms of human settlements. I think now is the time for question and answer session. I will read the questions that are posed by the participants to the panels, and the questions are on the chat box. The first one, I think, goes to Kate. It has to do with data maintenance, and the question reads, does the team responsible for instrument maintenance, I guess, stay for the whole year, and I guess it's Antarctica, or only for some time? I think Kate or Judy can answer this.
I'm happy to take the question, Summer. Yes, so we do send Antarctic engineers to overwinter, so they'll be staying there for 14 months. But there are team members that sometimes go just for takeover, which is from December until about February.
Okay, that will also answer the subsequent question about if it was only some time, what if there were unforeseen events that will occur and the instrument is damaged. So then, Douglas, there's always somebody there throughout the year who will look after the instrument. So the next question is, also you stated that bad data is better than no data. So I think it's the other way around. No data
Yes.
is actually embed data.
I hope I didn't say that wrong.
As a scientist, I think that's the one we will prefer. So the question from Douglas is, how do you clean data if it's corrupted? And how do you tell what is bad data or good one? Because you don't want to remove the useful, more especially if it's monitoring an anomaly.
Sure. Well, generally during the life of an instrument, they will have something we call a PI, as a principal investigator, and they are responsible really for the quality of those data sets. So they would be best placed to say that this is great data as opposed to this is really bad data. What our team in Antarctica does make note of is when they are having problems with the instrument, or when the instruments have had to be shut down due to bad weather. So those are also logged, in records that when you go to look back at the record sets, you can actually tell, well, let's ignore this period of data.
Okay, thank you. So Douglas's the next question is, I think it's quite confusing, but maybe you'll make sense of it. It says, during process whereby you are making the space weather map, how is made? Because if you try to monitor it below, ground-based observation will not cover such a large area. And if you put a satellite in the area, the charged particles will induce a current in the satellite, destroying it. So again, how is it done, or what instrument do you use? And also, how long can you continue to monitor, that is, make a map when it is occurring? Second speaker. So sorry, it's for Judy.
Sure.
Yes, okay. I'll just share my screen again of that map. Just so that we can look at it. Can you see the map again?
Yes, Judy, we can.
Okay. Okay, so how the map is made is it uses these measurements from all the different SuperDARN radars. So SANEA is just one radar that's contributing some of these vectors. But there are, as you saw when I showed you the map of different radars, there are about 13 in the Antarctic, and they're all contributing to these little dots and arrows. Then what we do is we apply a model to that data of what has happened historically in these conditions. And then the model works to best fit the data. So that's how we get the map, from nothing else but our measurements and a model of what has previously happened with similar conditions. So it's true, a satellite could not form a space weather map, because you'd have to have a number of satellites contributing measurements, all in the right place in the right time. And so it would be very difficult to produce a space weather map from a satellite, because one satellite can only give you one measurement at a time at one point in space. So that would be extremely costly. For a fraction of that cost, you can put these radars on the ground and create the same space weather map. And so I think SuperDARN produces the only space weather map in the world. So I hope that answers your question.
Thank you, Judy. The next question is from Nondumiso Kumalo and goes to Nale. Her question is, what satellite does EO use to take the images?
You can hear me?
Yes.
Okay. We use a number of Earth observation satellites. So these are the satellites that are facing or that are acquiring images about the Earth. So we use satellites such as Landsat, Sentinel, board and other very high resolution imagery like world view, which will allow us to see a lot of detail. So there are a number of satellites that we use, and which one chooses to use, it depends on the application that one wants to derive. We can also use the SAR, synthetic aperture radar satellites, to also assist or to process, to generate information about what is on the Earth or what's happening on the Earth. I hope that answers the question.
Yes, I think that actually gave quite sufficient information. Thank you. Again, the next question has to do with Earth observation, and it's from Douglas Moyeni, who asks, can one use Earth observation for economical advantages, such as checking which area has got a specific mineral or mining and etc., or is it only for population control, i.e. capacity limitation?
Oh, okay. No, we can use Earth observation for a lot of applications, including identifying areas with particular minerals of interest. So I think, yes, maybe the presentation focused a lot on population because the topic was more in terms of how we can use the data to shape our cities. But definitely there are other applications that we can use to get more information that can actually develop the economy. So there are sensors, hyperspectral sensors that we use to assess the minerals in particular areas. But of course, for such applications, there's also a need for some ground surveys due to the limitations that we have from the sensors that we have access to. However, if one is using, for example, if one has a sensor which can be on board an aircraft, it could then give enough information if it's a relevant sensor for mining. So no, definitely there are more applications, and it's, yeah, we don't really use, we promote not necessarily control, but it's more in terms of management. Even when we're looking at human settlements or distribution of people, it's more in terms of management and to make sure that people are living or situated in settlements, are situated in areas that are suitable for habitation, that are safe, and of course, that are closer to economic opportunities. I think what we are also trying to do with the data is to actually find a way to help authorities see how they can actually try and transform the settlements from the previous planning, which was really controlling in terms of where settlements should be or where people should be living, and make sure that the future development is taking place in areas where people will have access to services. So yeah, I think maybe let me leave it there. Thank you.
Thank you, Nale. I hope that answers Douglas Moyeni's question. And the last question, which goes to Judy, is how long has the SuperDARN been operating, and how many more years is it expected to operate? And it's from Anonymous.
Thanks for the question. Yes, it was actually, the first one was built in the United States. And so, of course, when the first one was built, it wasn't called SuperDARN because that's the name that came for the network. So, so the network started to form with about 7 radars, I think. That's when it became named as SuperDARN, and that was in the late 80s. And SANEA started, our contribution as South Africa started in 1997 So we're one of the older members. And in fact, our professor here was a founding signatory of the agreement. And how many more years is it expected to operate? Well, I would say it's not going to stop anytime soon, because our reliance on understanding space weather and preparing for it is just getting more and more urgent as our technology increases. So I would, and SuperDARN has been awarded many awards from NASA and the Royal Astronomical Society, many high-ranking science bodies in recognition of its contribution to space weather. So I don't expect it to stop anytime soon.
Okay, thank you. That answers Nundumiso's question, who also thanks you. I do not see any other questions on the chat box or a Q&A box, and therefore would like to bring our webinar to an end. And by thanking our speakers for today, thank you everybody for all your interesting presentations and information, and it's really has been eye-opening to see just the use of space weather and space information in our research, as well as in the development, urban development in our country. So lastly, just before we close, I'd like to remind the participants who are interested in the competition that the question for today is, what is the process through which the magnetic field in space plasmas reconfigure to release energy? And you can email your answer along with the 4 other answers to that were posted in our webinar earlier this week, and one question will be from tomorrow's webinar to space-info@sansa.org.za. That information again is posted on the chat box. Lastly, I would like to invite you all again to our last webinar in the World Space Week series, which will be tomorrow, and we'll be talking about space science or space from the classroom to the boardroom. It's going to start again tomorrow at 2. Thank you very much and have a lovely afternoon, everybody.
Bye, everyone.
Thank you. Bye.
Thank you. Bye-bye.